Researchers are testing a wingspan prototype of the X-48B, a blended wing body aircraft that may have military and commercial applications. Boeing Phantom Works partnered with NASA and the U.S. Air Force Research Laboratory to study the advanced concept fuel-efficient blended wing body. It is called a blended wing body because it looks more like a modified triangular-shaped wing than traditional aircraft, which essentially consist of a tube and wing with a tail. The big difference between this aircraft and the traditional tube and wing aircraft, apart from the fact that the tube is absorbed into the wing shape, is that it does not have a tail. Traditional aircraft need a tail for stability and control. The X-48B uses a number of different multiple control surfaces to control the vehicle. There will be a number of advantages to the BWB if it proves feasible. Apart from possible fuel savings of up to 30% due to improved streamlining, the interior of a commercial BWB airplane would be radically different from that of current airplanes. Passengers would enter a room like a movie theater rather than a cramped half-cylinder. There would be no windows or video screens would be connected to external cameras instead. And passengers would be seated in the large movie theater-like room because seating is not only in the central cove or core, but also well out into the blended wings. External flows are flows over bodies immersed in an unbounded fluid. The flow over a sphere and the flow over a streamlined body are examples of external flows which were discussed qualitatively in Chapter 2. More interesting examples are the flow fields around such objects as airfoils, automation, and airplanes. Our objective in this chapter is to quantify the behavior of viscous, incompressible fluids in external flow. A number of phenomena that occur in external flow over a body are illustrative of the sketch of viscous flow at high Reynolds number over an airfoil. The free stream flow divides at the stagnation point and flows around the body. Fluid at the surface takes on the velocity of the body as a result of the no-slip condition. Boundary layers form on both the upper and lower surfaces of the body. The boundary layer thickness on both surfaces in Figure 9.1 is exaggerated greatly for clarity. The flow in the boundary layers initially is laminar. Transition to turbulent flow occurs if some distance from the stagnation point, depending on free stream conditions, surface roughness, and pressure gradient. The transition points are indicated by T in the figure. The turbulent boundary layer following transition grows more rapidly than the laminar layer. A slight displacement of the streamline of the external flow is caused by the thickening boundary layers on the surface. In a region of increasing pressure, an adverse pressure gradient, so called because it opposes the fluid motion, tending to decelerate the fluid particles, flow separation may occur. Separation points are indicated by S in the figure. Fluid that was in the boundary layers on the body surface forms the viscous wake behind the separation points. This chapter has two parts. Part A is a review of boundary layer flows. Here we discuss in a little more detail the ideas introduced in Chapter 2 and then apply the fluid mechanics concepts we have learned to analyze the boundary layer for flow along a flat plate, the simplest possible boundary layer because the pressure field is a constant. We will be interested in seeing how the boundary layer thickness grows, what the surface friction will be, and so on. We will explain a classic analytical situation for a laminar boundary layer and see that we need to resort to approximate methods when the boundary layer is turbulent, and we will also be able to use these approximate methods for laminar boundary layers to avoid using the somewhat difficult analytical method. This will conclude our introduction to boundary layers, except we will briefly discuss the effect of pressure gradients that is present for all body shapes except flat plates on boundary layer behavior. In Part B, we will discuss the force on a submerged body, such as the airfoil. We will see that this force results from both shear and pressure forces.